Hi, this presentation is a preview of my tenure talk titled Decision Making for Many Mobile Objects. Let me start with what I do. In the past few years, I have been focusing on the algorithmic study of fundamental decision-making problems in robotics. To provide a sample, one of the main problems I have been working on is optimal multi-robot motion planning, where we want to quickly compute high-quality solutions for routing a large number of robots. I have also studied the multi-object rearrangement problem, where we want to compute effective plans for rearranging many objects. More recently, I started looking at high-level decision-making for multi-robot systems. For example, how can we deploy mobile sensors to best secure a perimeter or a region? For the problems we studied, we produce results of the following flavor. As it turns out, many of the decision-making problems that we study are computationally intractable. When this is the case, we prove that they are NP-hard or sometimes harder. Now, regardless of the hardness, we would like to solve these problems effectively. That is, we develop state-of-the-art algorithmic solutions for tackling these tasks. Now, these are a few examples computed using the algorithms that we have developed. Along the way, we have also developed several general methodologies and techniques that apply beyond the problems that we set out to solve. These include dynamic programming methods for task and motion planning problems in robotics, integer programming-based framework for path-based optimization problems that is both easy to use and produces high-quality solutions quickly. We have also developed novel divide and conquer techniques for multi-robot motion planning. After introducing what I do, I will outline the topics to be discussed in this presentation. Under the subject of collaborative autonomy, sitting at perhaps the lowest level is the problem of multi-robot motion planning. I say that this is at the bottom level because for each robot, specific start and go configurations are given. All we need to do is to plan paths for routing these robots. At a high level is the task assignment problem. Here, we must first match task locations with robots that we have. At an even higher level is the problem of deployment strategy generation. Here, only very high-level tasks are given. For example, a task may be deploy these mobile sensors to secure that region. We have also studied many interesting problems under the subject of multi-object rearrangement. One of these is the tabletop rearrangement problem, where we want to use a manipulator to rearrange many objects, for example, soda cans. Here, we can lift a soda can, move it somewhere else, and then drop it down. In solving the problem, we would also like to optimize some objective, for example, minimizing the number of pick and place operations. Another setting that we have studied is the stack rearrangement problem, where objects are now only accessible from the top of the stacks. We have also examined the clutter removal problem with applications to home automation and disaster relief. For all these topics, our study focuses on optimality and efficiency issues. That is, for the algorithms that we develop, we generally provide provable guarantees on these metrics. Along the years, I've also been involved in several industrial collaborative efforts, including warehouse automation and recycling automation. For the presentation, I will first provide a chronological summary of my research under these subjects of collaborative autonomy and object rearrangement. Then I will provide a very brief account of my industrial collaborative efforts. After that, I will highlight a couple of these topics with more technical details. Before moving on, I would like to thank my collaborators who have contributed to the works that I will be discussing today. I would also like to mention that for all the works that I will be discussing today, either I am the first author or a student of mine is a first author, with perhaps 2 exceptions. In these cases, I was a main contributor to the research. Now, I will provide a chronological summary of my research on the collaborative autonomy and multi-object rearrangement. The research that got me started on collaborative autonomy is Rendezvous Without Coordinates, where we characterized the conditions necessary to ensure that a group of Dubin's-Car vehicles will rendezvous under extremely limited sensing and control. A Dubin's car is a simple vehicle that can either move straight forward or turn left, right with a fixed turning radius with the same forward speed. For sensing and control, we assume that a vehicle has a windshield of some angle 2 phi. Right? So this is the windshield. It uses this windshield to track other vehicles as targets. Now, if the target is within the windshield, then the vehicle will simply move straight forward. If the target disappears to the left of the windshield, that is, kind of goes outside the windshield like this, then the vehicle will turn left until it sees the target again. The same applies to the right side. As it turns out, under this very simple sensing and control, as long as we control the windshield size properly, we can guarantee that the entire system will rendezvous in finite time, regardless of the pursuit topology. On the other hand, if the windshield size is above some threshold, then the system may diverge. We further show that the system can operate in a distributed manner. Each vehicle only needs to track the closest target. From there, I started examining multi-robot motion planning problems, which has 2 main flavors, labeled and unlabeled cases. In the labeled case, we have a set of robots, in this case 4 of them, with specific start and go configurations. We need to plan collision-free trajectories for routing these robots, either on graphs or in continuous domains. In the unlabeled case, we do not care about which robot goes where. We only need to move from one configuration or one formation to another formation. As mentioned, we've also studied task assignment and deployment strategy generation under collaborative autonomy. A first result that I obtained under labeled multi-robot motion planning is a hardness result. We show that we could reduce the standard 3-set problem to multiple optimal labeled multi-robot motion planning problems, showing that these problems are NP-hard. Shortly after that, I was able to construct an integer linear programming model for solving these optimal labeled multi-robot motion planning problems on graphs. I apologize for this somewhat bad animation, which I had not had a chance to fix. Nevertheless, our algorithms remain the best performing ones to this day, especially for very hard mixed-span optimization problems. We have many robotics labs around the world using our algorithms for planning tasks, for example, flying drones. As you can imagine, optimal labeled multi-robot motion planning has many applications, including coordinating mobile robots in warehouses, scheduling mobile carts for fulfilling grocery orders, and even in the manipulation of micro droplets. So here, we have some small droplets sandwiched between glasses and can be manipulated using static electricity. Now, these droplets may contain chemical or biological agents that can be merged and split to carry out reactions. If we can pack more of these droplets and move them more optimally, we can do more experiments faster, which is clearly desirable. So I will discuss the integer linear programming model in a bit more detail later. When it comes to the unlabeled multi-robot motion planning, we can actually solve some of these optimally in low polynomial time. For example, for this particular setting, we have about 140 robots moving between two formations. We could actually compute this solution, which is distance optimal, in about 0.01 seconds on a very old laptop. This may be somewhat counterintuitive, as it seems that we need to do more in the unlabeled case than the labeled case, since we must first do assignment and then motion planning. Now, the intuition behind the unlabeled case being easier is as follows. Consider we have, say, two robots, 1 and 2. In the labeled case, we might have the situation where we need to send robot 1 to 1 prime and robot 2 to 2 prime. In this case, we will have a conflict between robot 1 and robot 2. That is, they must run in opposite directions and potentially hitting each other. This will actually never happen in the unlabeled case, because in this case, we have the power to always assign robot 1 to go here and robot 2 to go here. So the ability to do assignment and motion planning together actually helps us. Let me erase these. So unlabeled multi-robot motion planning also has many applications. For example, coordinating the formation, flying of drones, and doing evacuation planning for buildings in case of fire. Later, we were able to extend the result and show that once we compute an initial plan, we can execute this plan in a distributed manner without loss of optimality. During my postdoc time at MIT, I extended the graph-based ILP model to work for continuous domains. We were able to push the supported density to 23%. That is, up to 23% of the free space can be occupied by the robots, and we can still guarantee a solution. If we do not want that guarantee, we can push the density to even higher. For the examples illustrated here, we could compute the solutions in about 1 to 2 seconds. The results are 1.2 to 1.3 optimal. A bit later, after joining Rutgers, I was able to strengthen the earlier hardness result to work on planar graphs. Because a planar graph is a special type of graph, the later result is stronger and implies the earlier hardness result, but not vice versa. The result also explains, to some extent, why it is a difficult challenge to solve the traffic congestion problem. COVID-19 seems to be a solution, but probably not a desirable one. On the continuous side, for the unlabeled case, we were also able to extend graph-based results to continuous domains. This is joint work with folks at Tel Aviv. After I graduated from UIUC and before joining MIT for postdoc, I did a very short postdoc working with Songju Chang and Petros Voulgaris. I proposed and worked on a stochastic assignment problem. Here, the setting is roughly as follows. We have some n robots and n targets, both randomly distributed in the same domain. Each robot has a sensing radius, within which it can sense the targets. Each robot also has a communication radius, within which it can communicate with other robots. Very briefly, we were able to come up with a decentralized policy or strategy for those robots to serve the targets with near-optimality guarantees. This is realized through the application of percolation theory and random graph theory. When I was at MIT, the lab I was in has a lot of facilities for making robots. So I spent some nights playing with these things and made this small wirelessly controlled car. This is enabled partly using 3D printing. It's about 4 centimeters wide and 8 centimeters long. At Rutgers, I continued working on the software stack and improving the hardware design. We have released this as an open hardware and software platform. The platform can do quite a bit of interesting multi-robot demonstrations. I would like to push this further in the future, potentially commercializing it for education and research purposes. At Rutgers, I tried to push more on the fundamental side of multi-robot motion planning. In a few years, I was able to push out a result that shows that we can compute constant factor optimal solutions for labeled multi-robot motion planning on grids of arbitrary fixed dimension in low polynomial time. This, in some sense, is a fairly tight result, since we have proven that solving the optimal labeled multi-robot motion planning problem on graphs is NP-hard. After joining Rutgers, I worked with my colleague Kostas Bakris on several object rearrangement problems. A first one of these is the tabletop rearrangement problem. As I have mentioned, we're allowed to lift an object off the table, move it around, and then put it down at an empty spot. The goal here is to minimize these pick and place operations to complete a given task. Now this might seem to be a trivial problem to solve. It actually is very hard. To provide some intuition behind the difficulty, let's look at this example here with these soda cans. So if we want to move the Sprite can, right, from its original location to the goal, right, we must move the Coke can out of the way first. On the other hand, if we want to move the Coke can, we must also first move the Sprite can. Now, with a single robot arm, we must then move either the Sprite can or the Coke can to a temporary buffer location. This will essentially add to the number of required operations. So this gives us what we call a dependency graph structure like this. So here the green one is the Sprite can, the red one is the Coke can. It turns out that if we want to minimize the number of operations, it is equivalent to finding the minimum number of vertices on this dependency graph we must remove to make it acyclic. This mirrors the well-known feedback vertex set problem, one of the first 21 problems proven to be NP-hard. This problem is actually even hard to approximate. Nevertheless, we were able to design heuristic algorithms, allowing us to quickly compute solutions for up to 20 objects. So this video here provides one example application of our algorithm. So we have also worked on versions of the tabletop rearrangement problem that applies to improving efficiency for pick and place tasks found in industrial applications. For example, picking and placing pancakes and packing of cookies. Let me erase this here. So another problem we examined in object rearrangement is the stack rearrangement problem. As we have mentioned, the objects are now only accessible from the top of the stacks. Under object rearrangement, we also look at the clutter removal problem, which I'll mention in a bit. For today, I will discuss these two problems in more detail. Before getting to that, I want to mention these two problems actually share some interesting common structures, which is not obvious from a first look. This is summarized in this Rubik table problem formulation, given an n times n square, filled with n types of items of n each. In a shuffle, one is allowed to take out a column or a row and permute that column or row arbitrarily. So the question is, how many shuffles do we need to be able to go from the start configuration to an ordered go configuration? It turns out that the Rubik table problem and associated algorithms are applicable to both multi-robot motion planning and stack rearrangement. Later, we pushed further the density that we can support to 51% for near-optimal multi-robot motion planning in continuous domains. Again, we have provable completeness guarantees here. More recently, we started looking at really making optimal multi-robot motion planning extremely efficient for larger environments and dynamic settings. We also started working on clutter removal problems. The goal here is to clear the clutter from some environment, for example, a room after an earthquake. We actually have gotten a somewhat negative result here. We were able to solve the problem near optimally using dynamic programming-based approaches. But it turns out, except for some very special cases, a very fast greedy approach actually does almost as well as our DP-based approach. So joke's on us. In late 2018, we started looking at high-level decision-making for multi-robot systems. A first line of research we did examines the problem of deploying a set of 1D mobile sensors for optimally guarding a 1D perimeter. Here, we're looking for one-point X globally optimal solutions. This is in contrast to control-based methods, which generally try to iteratively compute locally optimal solutions. For the case where the robots are homogeneous, we can solve the 1D guarding problem very fast, supporting millions of robots. Once we go from homogeneous robots to heterogeneous robots, however, the problem becomes NP hard. We could still solve practical problems in these cases, supporting around 100 robots. More recently, we examined the problem of guarding 1D perimeters or 2D regions using 2D range sensors. We obtained some results of similar flavor that were accepted by RSS 2020. So that was an overview of some of my research efforts in the past few years. Since joining Rutgers, with my colleagues, I have started tackling industrial projects. One of these is a warehouse automation task that we worked with JD.com to solve, where we use robot manipulators with simple suction cup and effectors to tightly pack products into boxes. We were able to design a set of motion primitives that together were able to realize very difficult packing tasks. For example, here we're packing 9 soap bars into a very tight space. We can do this freely, reliably, and robustly. Another project that is ongoing in my lab is a project with a large recycling company where we're tasked to modernizing their product lines. Here I'm showing a demo system where we have a robot arm spreading and picking scrap metals, which requires us to solve computer vision problems as well as manipulation problems. So there are some interesting research challenges here, though the majority of the efforts are engineering driven. I will discuss a bit more of these industrial collaborations in the future work section. Now, let me tell you about the Rubik table problem and some of its applications. Let me state the problem formulation again. We are given an n by n square filled with n types of items of n each. In a shuffle, we can take out a column or a row and arbitrarily permute the content of that column or row and then put it back. We ask the question of how many shuffles are needed for realizing an arbitrary reconfiguration. That is, the left configuration here can be arbitrary. It seems that you need at least 2n such shuffles, as it would appear that each row and column must be shuffled at least once. As it turns out, 2n is actually all we need to go from the left configuration to the right configuration. Now, once we have the configuration on the right, we can actually solve a fully labeled problem by permuting each column once. So we can solve fully labeled problems in 3n shuffles. Since this last step is clear, I'll only go through the proof of this theorem here. The key step to the proof is that we want to permute each column, so we reach the situation where the n items destined to go to a given column will end up in different rows. So we'll illustrate this using an example. In this 4x4 table, we have 4 types of colored items: red, green, cyan, and orange. For each type, we have 4 items. We would like to arrange them using column or row permutations to get to this ordered configuration. To do this, we first construct a bipartite graph, where one of the partite set is formed by the colors R, G, C, and O. The other partite set is the set of columns C1 through C4. We add an edge between a color and a column if the column contains items of that color. For each appearance of an item, we add one additional edge. So the red is connected to C2 once, C3 once, and C4 twice, because the red appears in column 2 once, column 3 once, and column 4 twice. We can do the same for green, cyan, and orange items. In the end, we get this bipartite graph, which is a regular bipartite graph. Next, we'll start finding perfect matchings on this bipartite graph. For example, a first matching may be this one. Based on this matching, what we do is we'll fill out a row of the next full configuration of the table. So we'll try to fill out this row here. So we have a green item matched to the first column. So we have this edge here, right? And we then put green in this first column here, and the red is matched to column 2. So we put the red in the second column, and we put cyan and orange in the third and fourth column. So once we are done with one matching, we'll remove this from the bipartite graph, and then we repeat the process to find another matching. So get another matching and then fill another row. We do this repeatedly until we exhaust all the edges. At this point, we observe that we get a new table where we can actually permute each column of the original table. Let me erase this. We can permute the column 1 here to go from here to here. We have 2 greens, 1 orange, and 1 cyan. We can certainly go from here to here using an arbitrary permutation. The same for the second column and the third column and the last column. That is, we can use n column shuffles to go from the first table to the second table. Now, in the second table, or the second configuration, it has the property that each color appears in each row exactly once. So we can definitely go from the second configuration to the ordered configuration using n row shuffles. So that is how we prove the theorem. Of course, with one more set of shuffles, we can solve the labeled version. So we briefly mentioned that we can add a further dimension to the Rubik table problem to get what we call a fat Rubik table problem. The same result actually would hold with an updated shuffle primitive, where we can now work with a fat column or a fat row. So that is the Rubik table problem. Next, we will see how the Rubik table results will help us with optimally solving labeled multi-robot motion planning problems. We examine here a most constrained case where all vertices of a grid are populated with robots. We want to go from an arbitrary initial configuration to an arbitrary goal configuration. For this problem, we have the following result. In an arbitrary fixed dimension, and constant factor mix-span optimal solution can be computed in OV square time for arbitrary start and go configurations. Here, V is the number of vertices on that grid, which is equal to the number of robots. So this is realized via the composition of two algorithms, split and group, or SAG, and partition and flow, PAF. So here, SAG gives us expected constant factor optimality. PAF uses SAG as a subroutine and gives us the true O1 optimality. Given the time that I have, I'll only highlight how SAG works. So given an instance of the problem on an M1 times M2 grid, one iteration of SAG works as follows. We split the grid along a longer dimension, in this case M2. Now this split induces a partition of the robots into two groups. Here, the orange ones are the ones that must go to the right side in the end, and the purple ones are the ones that must go to the left side in the end. For example, robot 4 should end up here, and robot 5 should end up here eventually. What we will do is to group these purple ones to the left side and the orange ones to the right. Here, we do not care exactly where a robot will end up, as long as the color is right. I claim that we can do this using M1 plus M2 steps. Now, if this is the case, then we can use this procedure iteratively and solve the entire problem. Note that in the second split, right, if we split along this dimension one more time, we need only OM1 divided by 2 plus M2 steps, and so on. So we have smaller and smaller number of steps that we need to carry out. So if we add up everything, we end up using a total of OM1 plus M2 steps, which is what we want. So all that is left is to prove that we can do this SAG iteration. So to carry out a single split and group iteration, we need some primitive operations. A first primitive is a constant step edge flip operation on a 2x3 grid. So we're given a 2x3 grid with 6 robots on them. What we do here is we first rotate these 4 robots along this cycle. So we rotate like this for one step. This will give us a configuration that looks like this. Now we rotate these 4 robots along this cycle, which will give us a configuration that looks like this. At this point, we rotate all 6 robots along this larger cycle, which gives us this final configuration. If we compare this with the initial configuration, we see that only robots 2 and 3 are exchanged. The location of all the other robots actually remain the same. So from there, it is clear that we can then do multiple of these edge flips again in a constant number of steps. That is, we can flip all these edges in a constant number of steps by partitioning the larger grid into a bunch of 2 by 3 grids and then do everything in parallel to get this new configuration. Finally, we can use these parallel edge flips to exchange 2 groups of robots on a path of length L. Here we can exchange the purple and the orange robots to get a configuration like this using only OL number of steps. With the primitives, we can then carry out the desired SAG iteration. We can apply the Rubik table result to the left half of the grid. With a column shuffle, we can go from the top left configuration to the bottom left configuration. This shuffle is done using the last primitive from the last slide. This is then followed with a row shuffle and then another column shuffle to get to this bottom right configuration. In this configuration, we note that for each row, the number of orange robots on the left is equal to the number of purple robots on the right. At this point, we can exchange these 2 groups of robots, again using the primitive that we described on the last slide. And this then completes an SAG iteration. So we can formalize this and show that this actually works even on high-dimensional grids. After multi-robot motion planning, next I will illustrate how the Rubik table result can be applied to the stack rearrangement problem. In a stack rearrangement problem, we are given n stacks of depth d each that are filled with n types of items of d each. We have an empty buffer stack. In a single operation, we can pop one item from the top of a stack and push that item into another stack that is not full. We would like to rearrange the stacks in this way to go from the left configuration to the right configuration, which is nicely arranged, while minimizing the total number of stack pop and push operations. The stack rearrangement setting does appear in practice. For example, at container ports, the containers are arranged in stacks. Only containers on top of these stacks are accessible. For the problem, we have some earlier results from our RAL 2018 work. We show that if we only want to do partial sorting, we can do that in OND log D, OND log n pop push operations. If we want to do full sorting, we can do that in OND log n plus log D steps. This compares with the straightforward lower bound of omega and d. We have also developed exact algorithms for solving the problem that scales to about 20 objects, which is practical. Here, I will highlight some recent development with my colleague Marius Zeddy, where we have the upper bound dropped to OND for almost all n and d. We have not fully closed the gap, but we're pretty close. Our approach is a recursive one. For any fixed n, we solve the problem layer by layer, first with d equals 1, and then square root of n, then n, and so on. I will illustrate here the case of d equals 1 and d equals square root of n, and the later cases are just recursive applications. As an example, when n is 16, the case of d equals 1 is pretty straightforward, so I will not discuss this in more detail. For the next iteration, we have d equals square root of n equals 4. What we would like to do here is to simulate fat column and row shuffles, so we can apply the fat Rubik table result. So what we do is we treat essentially the first 4 stacks as a fat column. We first take a single stack, the leftmost one, and empty its content into the buffer stack. And then this takes the OD number of pop and pushes. And then we take the top of these 4 gray stacks and move the content into the stack that was just emptied. So this again takes OD number of steps. And then we move the content of the buffer stack onto the top of these stacks, which takes again OD number of steps. And then we repeat this process. We can then move the content of all the red stacks to the top of these stacks. And then, in another OD number of steps, we can rearrange these red cells arbitrarily to get new arrangement any way we like. So this is essentially applying this result here. And then we can return the content by reversing the operations and get some new arrangements of these stacks. So up until now, we have completed the simulation of a fat column shuffle, and we take only OD squared number of steps. So essentially, we can treat every 4 consecutive column as a fat column, and then these scattered columns, scattered stacks, as a fat row, and we can then apply the Rubik table result to get what we need. After discussing some more fundamental results, I will switch the gears a little bit and discuss a more applied result of using integer programming methods for solving path-based optimization problems in robotics. Our basic approach transforms a multi-robot motion planning problem into a multi-commodity flow problem over multiple time steps. So, given a multi-robot motion planning problem, we take a copy of the vertices of the underlying graph and make multiple copies over different time steps. We then connect these copies using specially constructed edges that translate to binary variables, where if an edge is used, the corresponding variable will take a value of 1. We then add the start and go configuration into the mix and add additional collision avoidance constraints to build a complete model. After working with IP-based methods for a while, we were able to generalize them to obtain an IP framework that applies to a variety of path-based optimization problems, including multi-robot motion planning, minimum constraint removal, and reward collection problems. Overall, the framework is a good first option for many path-based optimization problems. So if you have such a problem that can be discretized, you can perhaps give our method a try. Often it works quite well. So now let me provide some computational results of our IP model for solving optimal multi-robot motion planning problem on graphs. So we're trying to solve problems that looks like this, where the white robots are the go locations and the shaded ones are the start locations. So we can compute exact optimal solutions, exact make-span optimal solutions for up to about 100 robots in under 100 seconds for a variety of problems. And if we add some additional heuristics, we can push the number of supported robots to be really high, to about 180. And we can also at the same time reduce the time to mostly under 10 seconds. And the optimality that we get is quite good, often below 1.05 optimal. I want to mention that we actually support very high robot density here. So at the extreme, we can solve problems with 44% of robot density, whereas in settings like this, the density is only 15%. You can imagine 44% is really high. Our ILP framework has found many applications. It is especially effective for finding initial solutions that are near optimal for solving more complex problems. We have used it ourselves for solving dense 2D problems in continuous domains, as I have mentioned earlier. Our methods have also been adopted by many other research labs around the world. For example, folks at USC have used our methods for planning base paths for flying a large number of the Crazy Fly quadcopters. At MIT, people have created a hybrid vehicle that attached wheels to the Crazy Fly quadcopter. Once again, they used our methods for compute initial trajectories for scheduling these vehicles. Our ILP method has also been used for computing initial solutions for solving multi-arm manipulation tasks. I will conclude the presentation with a discussion of some future directions. Under the subject of multi-robot motion planning, on the more fundamental side, I'm working on establishing finer theoretical limits, for example, closing gaps that exist in our current results. I'm also working on developing algorithms for general graphs and general domains, i.e. beyond grid-like settings. Along the way, I also see new tools, techniques get developed. On the side of computational methods, we'll keep improving our existing algorithms and developing new ones. We will also explore hardware-based acceleration for further boosting the computational performance. For the topic of general high-level decision-making, I'm working on integrating decision-making and plan execution. I would also like to gradually explore more and more dynamic tasks, for example, guarding a set that morphs over time, or tackling more general tasks like enclosure, search rescue, search capture, and so on. I'm also exploring working with heterogeneous systems, for example, mixed ground and aerial robot teams, or human in the loop, and so on. Under the subject of rearrangement and manipulation, we're working on fundamental problems including the continued study of the intricate dependency graph structure and the generalization of the stack setting. In a stack rearrangement problem, objects can only be accessed from the top. We can explore other settings. For example, objects may be stored in a queue that can be accessed from both ends. We're also working toward turning our work into real systems. Currently, we're developing a hardware platform for clutter removal that will be able to do autonomous navigation, scene understanding, and precise pose estimation of target objects, and so on. We're targeting multiple application domains, including the household setting and the disaster relief-like settings. We're also generalizing the current work to be applied to multi-robot systems. Toward making broader impact, I'm working with collaborators on the automation of hazardous tasks, including warehouse automation and recycling automation. For recycling automation, we're adopting our scrap metal separation demo system to produce a conveyor-based production system. We're also working on the grasping of irregular parts for automating parts loading tasks in recycling. As I mentioned, I'm currently developing a multi-robot system stack that will have an open hardware and software design that is also customizable. The system will have a 1 meter square small footprint and will be highly affordable. Currently, each car, the latest V3 version, costs about 50 USD. In the target platform, we'll aim for a 6-car system costing less than 100 USD. The platform will be education focused in the beginning and targeting K-12 students. With that, I conclude this presentation. Thank you.